So today we're going to look at how to calculate the energy released from fission and fusion reactions. And at the end of the video, we're going to compare which of these reactions releases more energy. So let's first look at the fission reaction of uranium-235. So on the left-hand side of the equation, we've got the reactants. We've got uranium-235, and the 235 tells us that there are a sum total of 235 neutrons plus protons in the nucleus, and the 92 represents the number of protons in uranium. And this uranium nucleus is going to come into contact with a neutron. When this neutron is absorbed into the uranium nucleus, the uranium splits into two daughter nuclei, the barium here and the krypton, which are the products on the right hand side. And we also have three further neutrons being ejected in this process, and some energy is released as well. So in order to find out the amount of energy released in this fission reaction, first we must know the masses of the nuclei and the neutron, and we're going to represent these masses in atomic mass units. And as I've explained in a previous lesson, which you can view in the card above, one atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. So if we draw up a table here, our neutron has a mass of 1.009 atomic mass units. The uranium has a mass of 235.123. The barium has a mass of 140.912. And the krypton has a mass of 91.913. And these are in atomic mass units. Now, during this nuclear reaction, we expect the sum total of the mass on the left-hand side to be different to the sum of the masses on the right-hand side. In other words, there's going to be a mass change during this reaction. So if we add the mass of the uranium and the neutron on the left-hand side, their total mass should be different to the sum total of the masses on the right-hand side. So this change in mass has been converted into energy, and we can find out how much energy is released from this reaction by using Einstein's equation E equals mc squared, where the delta m in this equation is our change in mass during this reaction, and c is the speed of light. So with all the information on the screen, we have everything we need to calculate the change in mass as a result of the fission reaction. So what's the first thing we need to do to find this change in mass? Well, let's first sum up the mass of the reactants on the left-hand side. So uranium-235 has a mass of 235.123, and the neutron has a mass of 1.009 atomic mass units. And we get a total on the left-hand side, and we get a sum total of the mass of the reactants of 236.132. Now the total mass of the products, the barium, the krypton, and the three neutrons, all sum to 235.852 atomic mass units. Now we can see here that there is in fact a drop in mass during the fission reaction, and we can calculate this mass change by subtracting the mass of the products by the mass of the reactants. So 236.132 minus 235.852 gives us a mass change of 0.28 atomic mass units. And we're ignoring the masses of the electrons here because their masses are so small that they won't change the result that much. How do we now calculate the energy released? Well, if we go back to our equation E equals mc squared, we already know what the speed of light is, and we have our change in mass, so we should be able to find the energy released during this fission reaction. But to get our results in joules, our energy in joules, we need to convert our delta mass into kilograms. So let's plug this into our equation. 0.28 atomic mass units multiplied by 1.66 times 10 to the minus 27 kilograms multiplied by the speed of light squared gives us an energy release of 4.2 times 10 to the minus 11 joules, to two significant figures. Now we're going to have a look at a fusion reaction that is occurring in a center of a star. In this reaction, a deuterium nucleus and a proton fuse together to form helium-3. The binding energies per nucleon of deuterium and helium-3 are 0.864 mega electron volts and 2.235 mega electron volts respectively. So we covered binding energies in a previous lesson, and I'll link this in the card above. And the binding energy per nucleon is the total amount of energy required to completely separate all the nucleons in a nucleus divided by the total number of nucleons in that nucleus. And the higher the binding energy per nucleon for a single nucleus, the more stable that nucleus is. And this is because more energy is required to separate out the protons and neutrons from that nucleus. So how do we write this fusion reaction as a nuclear equation? What would our reactants be on the left-hand side, and what would our final products be on the right-hand side? Well, the reactants are deuterium, which is a hydrogen nucleus, so one proton, but also one neutron, because we've got a mass number of 2 here. And we also have a proton. So when these nuclei fuse together, we end up with helium-3. Now helium has 2 protons in the nucleus, and the 3 tells us the total number of nucleons in the nucleus. So if there's already 2 protons in helium-3, and there can't be any more protons or any less protons than that for this element, otherwise the element would change, then we know that the third nucleon must be a neutron. So this is the product in our fusion reaction, and we also release some energy. So we've got the binding energy per nucleon for the deuterium and helium-3. How can we calculate the energy released in this reaction? Now we need to remember that the binding energy per nucleon is the amount of energy required to separate out all the protons and neutrons in the nucleus. In other words, completely break apart the nucleus, and then we divide this by the total number of nucleons in the nucleus. So what we actually need here is the total binding energy of the nucleus. We've already got the binding energy per nucleon, and we've got the number of nucleons. We can rearrange this equation to make this total binding energy the product of the equation. So we end up with binding energy per nucleon multiplied by the number of nucleons in the particular nucleus we're studying. So for the deuterium atom, we've got 0.864 mega electron volts multiplied by 2 nucleons, because we've got a proton and neutron in deuterium. This gives us a total binding energy of 1.728 mega electron volts. And for the helium-3, The binding energy per nucleon is 2.235 megaelectronvolts, and we have 3 nucleons in helium-3. We've got 2 protons and a neutron. So the total binding energy for helium-3 is 6.705 megaelectronvolts. And again, this binding energy that we're calculating is simply the amount of energy required to separate out all these neutrons and protons from the nucleus. And you can see here that it takes more energy to separate the nucleons from helium-3 than it does to separate the nucleons from deuterium. For the proton, the binding energy per nucleon is 0, and we've left this out here for this reason. This single proton is not bound to any other neutrons, and therefore there are no bonds to break. Because there are no nucleons to separate out here, there is no energy required to separate anything. So the total binding energy for the proton would be 0. So the energy released in this fusion reaction is the increase in the total binding energy. And this is because energy is released when nucleons become more tightly bound. So if we were to think about it more carefully, if we want to break apart all the nuclei on the left-hand side of this reaction, we would need to spend 1.728 megaelectronvolts to do this, to separate all the particles that exist in the reactants. But when we fuse everything together into helium-3, our product on the right-hand side, in order to separate all the nucleons in this nucleus, we have to spend even more energy, 6.705 megaelectronvolts. The energy released in this reaction is the difference between the total binding energy of the reactants and the total binding energy of the products. So 6.705 megaelectronvolts minus 1.728 megaelectronvolts gives us an energy difference of 4.977 megaelectronvolts. Now, if we want to convert electronvolts into joules, into units of joules, 1 electronvolt is equal to 1.60 times 10 to the minus 19 joules, to 3 significant figures. So 4.977 megaelectronvolts, and megaelectronvolts means a million electronvolts, then multiplying 1.60 times 10 to the minus 19 joules by 4.977 megaelectronvolts, we end up with a value of 7.96 times 10 to the minus 13 joules. And that's the energy released during this fusion reaction. We can see from our energies from both the fusion and fission reaction that the fission of uranium-235 released much more energy than the fusion reaction. And if we want to figure out how much more energy was released, we divide the energy released by the fission reaction, 4.2 times 10 to the minus 11 joules, by the energy released from the fusion reaction, 7.96 times 10 to the minus 13 joules. And we find that the fission reaction has released 53 times more energy, to 2 significant figures.